It is quite easy to think of two objects at different temperatures exchanging energy until they reach the same temperature. But real-life situations simply aren't like that. Each object exchanges energy with all the others around it. If all these items are left to stand, the ice will warm up and melt. The hot coffee will cool down, and the stove, if turned off, will cool to the temperature of the room. Even the room temperature can change depending on the time of day. But sometimes we try to keep things from exchanging energy with one another. We have all sorts of ways of insulating the contents of everything from buildings to everyday containers so that limited energy can enter or leave. Huts in the rural areas of our country are designed to keep internal temperatures fairly constant through the changing seasons. The vacuum flask is another example of insulation.
The vacuum flask consists of two silver glass plates, one inner plate and an outer plate. And between them, we have removed the air molecules and have created a vacuum. This reduces heat loss as a result of convection. The glass plates are coated with silver inside as well. This reduces heat loss because the radiation occurs internally between the two glass plates so that no energy or little energy is transferred to the outside.
A rubber stopper also limits energy losses through conduction. Thus, the vacuum flask approximates to a closed system.
The closed system that we're referring to heat transfer refers to an isolated closed system where no energy is lost to the environment or no energy is gained by the environment.
Closed systems are vital in scientific laboratories where energy exchanges between bodies need to be measured exactly. In a classroom context, it is hard to create a closed system, but a reasonable approximation of such a system can be created for learners to investigate energy exchanges. Nkosinathi Shandu is teaching a lesson about energy exchange to a class of some 70 learners in Umlazi, Durban. The outcomes planned for the lesson in this video are for learners to understand the need for a closed system for accurate measurement of energy exchange, to set up and use approximations of closed systems for energy exchanges, to carry out a practical activity to calculate the specific heat capacity of a metal. The teacher first probes the learner's knowledge of energy from everyday experience.
Now, firstly, can you tell me how does heat contribute to our daily lives?
We cook.
How do we use heat then when we cook?
Stove.
We use a stove, okay. What else are we using at home which uses heat, yes?
Making tea.
Making tea. What do you use also when you're making tea?
We use a kettle.
Yes. And what else? Yes.
We use a heater.
Now we know now.
Once the teacher has placed the topic in the context of the learner's experience, they can use the class to build on their prior knowledge. The teacher then sets up the topic of the lesson as energy transfers between objects.
There is a heat transfer.
To give the learners an example of energy exchange, the teacher then heats up a piece of metal with a gas burner.
Here we go. Putting the metal into water, what happened to the temperature of both the water and the metal?
The temperature of the metal decreased and the temperature of the water increased.
Is the temperature of the metal and water the same now?
The learners respond in the affirmative.
Now we're going to look at an experiment where we're going to consider some containers. I've got different containers now here.
The containers are made of a variety of materials. Some are insulated, some are not. Some are sealed, most are not. The teacher gives a representative of each group a different container and then gives them very hot water in a beaker to be poured into their containers. They take an initial reading of the temperature of the water when the teacher gives them the signal. They then take readings of the temperature of the water every 2 minutes for the next 18 minutes. The teacher gives them the cue each time. The teacher moves among the groups, checking that they are taking the readings correctly.
Group A, they were using an open thermo flask.
When the 18 minutes are up, a representative of each group records their sets of readings on a table in front of the class. At the same time, each learner in the class draws a graph based on the readings of their group. The group representatives then transpose their figures onto a communal graph to generate a set of cooling curves for the different containers. A cooling curve displays the temperature of an object as a function of time. The teacher helps the learners understand the meaning of the curves better by picking some out for comparison.
This one now here, this one of an open polystyrene, and the other one of a closed polystyrene. Which one is cooling faster? Is it the closed or the open polystyrene?
It's open.
The teacher helps the learners recognize that the open polystyrene cup has a steeper cooling curve than the sealed cup, reflecting the fact that it cools more quickly.
Polystyrene minus.
He underlines this by comparing the decrease in temperature in the water in the two cups over the 18 minutes. The water in the open cup decreases by 22 degrees, the water in the closed cup by 17 degrees. He then shows how different materials affect the rate of cooling, comparing polystyrene and tin.
If you take a polystyrene, then you compare it with tin. Tin is giving heat to the surroundings faster than what? Than a polystyrene cup.
The teacher then tells the class they're going to work out the specific heat capacities of a variety of metals.
And can we predict which of the metals will cool first? Which one?
Aluminium.
Aluminium.
They then create a list of the metals in order of the predicted rate of cooling. This list will be tested against the actual result of their experiment. The teacher goes through the instructions listed on the board. He then distributes a beaker of water at room temperature to each group, and each measures out 150 milliliters of water. The teacher assists to ensure that the measurement is accurate. Each group then pours their water into an empty polystyrene cup, which they seal with a lid. Following the instructions on the board, they then take the temperature of the water and record the reading on their table. The table contains two columns, one for water and one for metal. The different headings are the start and end temperature, change in temperature, the mass, and the specific heat capacity. The learners are aiming to find out the specific heat capacity of the metal. The teacher then heats the different pieces of metal in a beaker of water. He places one piece in each group's cup of water in turn, at the same time calling out the temperature of the water in his beaker.
87 degrees.
The learners then record this as the starting temperature of their piece of metal.
When your metal...
The teacher then allows time for the water and metal to reach the same temperature.
I think by now you must read the final temperature of water and the final temperature of the metal.
The learners then take the final temperature of the water and also enter this as the final temperature of the metal, as the two are now equal. Before the learners can calculate the specific heat capacity of the metal, they need one final measurement, the mass of the piece of metal. They first balance the scale, then add the metal and take the reading. Once the teacher has given the learners the specific heat capacity of water, the learners have all the information necessary to be able to calculate the specific heat capacity of the metal they are handling. Their calculation is based on the premise that the energy gained by the water is equal to the energy lost by the metal, as a sealed cup is treated as a closed system for the purposes of the experiment. It is also assumed that the cup itself absorbs no energy from the water.
Any group can give me any value that they have for the temperature change.
We have 3 degrees Celsius.
3 degrees Celsius.
Yes, sir.
Are we going to be able to calculate the heat gained by water?
They calculate the energy gained by the water by multiplying the specific heat capacity of water by its mass and the change in its temperature. They know the mass of the metal and the change in its temperature, so they are able to calculate the specific heat capacity of the metal their group worked with. Once the teacher has checked each group's calculations, the class compares the actual specific heat capacities of the metal against what they predicted. The teacher then rounds off the lesson by emphasizing that every substance has its own specific heat capacity.
Given the fact that they are not used to handling these things, especially apparatus. So, but the way they did, the way they performed to me, it was quite extremely well.
One of the benefits is where they acquire skills in using measuring instruments and in actually working out the difference in temperature using a thermometer. And this helps them to understand that heat exchange is primarily due to a difference in temperature between a hot body and a cold body.
Hello, we have Mike from the School of Physics at Wits, and then we have Andrew from Protect, a well-known NGO. We are going to reflect on the video that we have observed, and this is one of the situations or some of the situations in which we find our teachers in our country faced with in the townships where they have 70 learners and they are supposed to do hands-on lessons. And we have seen this teacher trying to do or engage the learners into hands-on activities. And how do you think it has been done in this class of 70 learners?
What impressed me about this lesson was obviously a tremendous amount of thought had gone into it and planning, and the teacher was very, very organized throughout. He had to be because of the size of the class. He guided the learners all the time. The learners knew what they had to do, and so there was a great degree of structure, or a great amount of structure in the lesson. It wouldn't be what I would call discovery learning. I think it was more prescriptive, but I think for large classes one has to work in that way.
Yeah, I think I'll agree with what you're saying, because at some stage he kept on saying, look at this, what is happening here, write down, record, etc. So he kept on guiding them on what to do. And do you think is this one of the things that you can do in promoting group work or hands-on in our large classes in the townships?
Yes, Tembi, quite a challenge for most of our teachers, for us, dealing with those large classes. But I was also impressed with the way the teacher rose up to deal with that challenge. And the idea of a question, posing a question, its investigation is very much in line with the scientific method, There's always questions. Science is always looking to find solutions to problems out there. And therefore, it's a very scientific approach. If you think backwards, if you go back a couple of years back, when our teachers would walk into a class basically with a piece of chalk and just say, well, this is it, specific heat capacity, energy transferred is equal to, and write all that formula down, and learners had to road learn that. That's not a very effective strategy. I think we're seeing here a strategy more in line with the scientific method, the way scientists do things, asking a question, posing a question, and guiding the learners through practical actual activity towards coming up with a scientific theory.
And then in doing these activities, there were 2 or 3 learners that were actually touching because of the large numbers of groups. How do you think teachers can make sure that every learner is learning or is touching or is handling the equipment in such groups?
Each learner could be given a specific task. I guess this is the only way, unless a learner knows they have to do something specific, they could very well just melt back into the background and just leave it to somebody else, simply watch. So once again, this requires very, very careful planning strategies. Each learner should be given or designated a role. But also in moving from one experiment to another experiment, roles need to be exchanged. Otherwise they will not learn all the skills. You cannot have a situation where one learner is always acting as a recorder, and somebody else is always taking the temperature readings. They must swap around, or can even swap around within the experiment. So each learner has had an opportunity perhaps to take one temperature reading, to plot one point on a graph, to tabulate something in a table of readings, etc., etc. In this way, the skill acquisition can be shared fairly.
I've had the privilege of working also in the UK, Tembi, with some schools there, in a place called Cranford Community Centre, and it's interesting. One of the things I found there is that some of the classes were quite huge because this was a community school, you know, but one thing that really alleviated the pressure a lot was the fact that teachers had actual lab assistants, and I found that to just introduce something into the whole situation that just makes life so much easier for the teachers, and so that would facilitate the teachers to be able to deal with groups and make sure that learners are individually active within the groups, you see. And I think in this country perhaps that's something that we need to consider, a proper lab management.
Looking at the video as well, the teacher managed to take the learners through certain scientific processes of measuring, comparing, etc. But he even took it further to very advanced science skills of interpretation of data using a graph. And in my thinking, the amount spent on that was not enough.
My personal experience is that this is a skill which learners battle with, and it seems to be a skill which is perhaps under taught or under exercised. And you know, speaking as a science teacher, I always felt that in the mathematics they did not spend sufficient time in the plotting of accurate graphs relating to real situations.
I think I agree with what you have said, because also looking at the students that come to the university, they still battle with the actual plotting of the graphs. So
something as simple as choosing a scale, for example, even up to first year university sometimes, you know, learners can have problems with that, and I think it's very important for teachers to take cognizance of that and to actually spend some time developing some of those skills.
And then also going back to the practical work, learners in that video were writing and they were recording on some information as individuals. Although they were working in groups, they were recording as individuals. And then my concern will be, does a teacher have time to look at all their books where they are recording their information and actually do a follow-up whether what they have written on their books is actually correct?
It's extremely difficult, almost impossible, for a teacher to check you know, all 70 lab books or whatever they call that. But perhaps he could make use of peer teaching. Perhaps he could check one book from each group and then insist, and that is like the monitor book, that the other learners must make sure that the information which had been corrected by the teacher is then corrected for themselves from that book. That is just a you know, one amongst many suggestions which I could offer there.
I think at the end of the day, you know, the lesson was a success. You know, I would say to a greater extent, because I mean we should never forget that we're looking at energy transfer, this thing called energy, which we don't really know what it is, you know, but we can talk about energy transfer. We can talk about changes in the temperatures and how those are related, and how different substances, you know, lose. When one substance loses energy, another one gains energy. That there's something in between there, and this something that is transferred is what we label as energy. I think that was very well developed in an overall sense. But just I would concur with Mike. Very difficult. 70 learners. Very difficult to do everything.
And I also think the teacher did well by bringing various containers and actually
Yes,
let the
yes.
learners observe how much
Yes.
of those containers will lose heat
Yes.
easily, etc. So that was a very good
Yes.
idea to use everyday experiences
Yes.
Yes.
of the learners.
And also what was interesting, he did the heat exchange in a simple polystyrene cup. Again, one doesn't need sophisticated apparatus, the old style, double calorimeter lagged
Yes.
between the two,
Yeah.
which used to be available. For financial reasons, it's impossible to kit all schools out with that. So it just shows you can use a polystyrene cup to do very respectable physics, and I think that that was a good point. Just another thing I forgot to mention earlier was he did encourage the learners to make a prediction about the relative thermal properties of aluminium, iron, etc. And that was a good point too.
And also at the end, also he did record on the chalkboard the results from the various groups, and I found it very good because in some cases, when we engage learners into practical work, they do practical work, and the teacher, in most cases, does not summarize or give a summary of what has been happening in various groups.
So I think that's very important. I think the two things about experimental work, I think the first thing is there must be a clear aim to the experiment. There must be a very distinct reason why the experiment is being done. Otherwise it becomes a rather wasteful activity. The other thing is, as you said, there must be a pulling together of what the experiment was about, because otherwise, again, the purpose is lost.
Okay. And also to add on what you're saying, also having done that, also link what has been happening or what came out from their investigation with the concept that the teacher is trying to introduce. That's very important as well. Okay, thank you very much. I think our time is over. And thank you very much for your participation. To the viewers over there, thank you very much. And that's what we have for you today.